Before we move on to the insertion and deletion operations, I would like to recap about the searching operation, and most importantly, I want to do some quick comparison with how we perform the binary search on a sorted array. That will be quite important as well. You might be wondering as well if you actually have been thinking about what we are really doing here. We'll see. Right, so recursive call for the search are really made on a path for the binary for the search through the binary search tree. So start from the root, and also you want to go down one level at a time. So this is really the critical insight. And for the slides over here, it's just about summarizing what we said already. And ultimately, you want to understand that if I'm only telling you the input is a binary search tree without telling you whether or not it's balanced, in that case, the safest answer will be big O of H. But if I can give you more information, you can definitely say more. Let's talk about them right now. And remember, given n nodes, we know that the height of H is really bounded by log n and also big O of n. Right? That's the property of the binary tree that we spoke about before. It's definitely applicable. So that's why we spoke about the mathematical property for the binary tree earlier. So now we can definitely apply them. So this will be the worst case big O of n for searching through a binary search tree, in which case the tree is not balanced. On the other hand, the best case we can reach for performing a search on a binary search tree will be log n. Right? You can see the H. We're talking about H. That's a lower bound for the best case and the upper bound for the worst case. Right? Best case and worst case. And just notice that for the best case, it is when the tree is balanced. And for the worst case, it is when the tree is ill-balanced. Okay? That's something I'll give you some visual example today, this week, just to for you to get some intuition about what it really means for a tree to be balanced versus ill-balanced. But for next week, when we move on to the next lecture, we're going to talk about the balance property for binary search tree. We'll get there a little bit later. Right? This table here is very important. I'm going to go over. You can definitely study the table yourself. I'm going to give you some visual illustration about the points that's being made on the table. We want to compare two cases. Whenever you talk about some search operation on a binary search tree, which may or may not be balanced, you want to compare that against the case where you try to do a binary search tree on a sorted array. Okay, let's now talk about it. Okay. And the title here really also suggests something that we have been emphasizing. We're talking about non-linear, which will be the case of searching through the binary search tree, and also linear structure, in which case we're talking about searching through, performing a binary search on a sorted array. Okay, that's something very important. Let me make a note right away. The assumption that we are making. And this one over here is a binary search tree. And of course, this one here is just another binary search tree. I'll talk about what the difference is between the two. And this one over here is a sorted array in the non-descending order. And of course, these two are non-linear. And this one over here is linear. Let's now talk about the difference between these two trees very quickly. Okay, this one is more or less what we call balanced binary search tree. More or less. Let me put it here. This one is what we call balanced, meaning that the height of the tree is roughly log n. Okay, we can try to take a look very quickly. You can see how many nodes do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? So if you try to see log, for example, log 15 is going to be less than 4, roughly about 3 point something. Right? Because 2 to the power of 4 will be 16. So 3 point something. And if you try to look at about the depth of 3, so this would be depth 1, depth 2, depth 3. So basically we talk about level number 3. So level number 1, level number 2, level number 3. Over here, around here. Most of the nodes are before or on level number 3. So that's why we can say this tree is close to be balanced, but strictly speaking, it's not exactly balanced, as we'll see the strict definition next week. But at least if you compare this tree over here and this tree over here, at least we can say it's more balanced. Okay, let me just make it clear to you. You can think about it is actually more balanced. It's very close to log n, very close. Okay, because log n will be around over here. This will be when the depth is actually equal to 3. Alrighty. And what about the other tree? The other tree is what we call EO balanced, not balanced. Let me write it down over here. So this one over here is EO balanced. I try to draw it in a way, it's basically almost like a one-pass tree. You can see on this branch, by the way, it's still a binary search tree. Why? If you try to do an in-order traversal on this tree over here, you're still going to get a sorted sequence. So this is still a BST. Don't get me wrong. Okay. However, given that these two trees actually store the same set of keys over here, however, their shapes are very different. One is much more balanced than the other one. And what about how bad is this? It's so bad such that let's say if I want to search for the key 8, what will be the worst case? The worst case is no longer log n, because if I want to search starting from 54, for example, let's say I want to search for example, 8. That one there is going to lead me all the way down to the 8 over here, right? And how high is this? This, I can tell you that this occupies almost about half of the nodes. So this is really about big O of n over 2, which is big O of n. So this is really kind of the worst case I was talking about. So this will be big O of n. On the other hand, if I want to search for the same nodes over here for 8, in that case, if I want to go from here all the way to 8 over here, so that one there is really big O of log n. Right? You can see the difference over here. The point is, when I try to make a search, even through the same contents of the binary search tree, depending on the shapes of the tree, either balanced or not balanced, the running time can be very different. It can be log n in the best case, or it can be n in the worst case. That's about a tree search. Very important for you to see. All right. And this one is also about searching for the key, maybe 8. You can see for between the two, the outcome is the outcome will be the same. You're just returning that internal nodes, but the running time will be very different. You'll be log n versus linear. Now, I want to draw the connection to this sorted array over here. Before I start my illustration, I'll really encourage you to pause the video and think about the following question I'm going to pose to you. We talk about either balanced search or unbalanced search. When we talk about doing a binary search tree on a sorted array, is it more analogous or is it more similar to a balanced search? Or it is more similar to an unbalanced search? Or both? Or neither? That's my question. You can now pause the video and think about your answer. Alrighty. Assuming that you thought about it, it's very important for you to think about, even though you may not be sure about what the answer might be, but I think it's really worth thinking about. The answer is, when we talk about performing a binary search on a sorted array, that one is really equivalent to when you are trying to search through a balanced binary search tree. Okay, let me talk about it. Okay. Let me first of all draw the conclusion, and I'll show you exactly how it can be thought about, how it can be visualized. A binary search tree, a binary search on a sorted array is equivalent in terms of the running time to, as far as running time is concerned, a search on a balanced BST. Let me highlight what's really important over here. We're talking about a normal binary search on a sorted array. as far as the running time is concerned, it is equivalent to a search on a balanced BST. And here I want to emphasize again, we talk about the balance, and I promise I'm going to go over with you about what balance property really means formally next week. Okay, and let's see why this will be the case. Right, this is the conclusion. Let me now try to visually justify it. Let's try to recall exactly how the binary search is supposed to be performed on a sorted array. We choose some initial value that will be sitting exactly in the middle. Remember, index 0, index 14. Add them up and divided by 2, which will be 7. Right? So index 7 should be where we start with. If you say we start with 7 over here, and then we say 54. Whatever key you want to search for, either we will go to the left half of the array or right half of the array. Either way we go, the other half that can be ignored is going to guarantee our search space is really reduced by half. Okay, let's say, for example, if we chose to actually go for this way, let's say hypothetically, let's say the key we want to search is actually strictly larger than 54. Right? Let's say if we go this way here, okay, recurring on the right half. I'm writing out of space. I'm going to write here. On right half guarantees the search space is reduced by half. Right? So the important point to note over here is about the search space. The search space is guaranteed to be reduced by half. Right? Let's say if we go for this way over here. And we keep doing this until we actually hit the item, or we don't hit it. In that case, that'll be unsuccessful search. That's why the number of decisions we have to make to either go to the right or to the left will be log n. So that's why eventually the log n, eventually the running time for performing the binary search on the sorted array is always big of log n. That's something to review, right? That's why I said to review. Okay, and this means the running time, better to put in green because it's good running time. That means the running time is always big O of log n, always, guaranteed, because we always reduce the search space by half. Why is this corresponding to? Why is such a search on this linear structure over here corresponding to a balanced binary search tree search? The reason is we will start with the root over here, and then going to the right half of the array is like going to the right subtree over here. If you go to the right subtree, what does that mean? That means you can safely ignore, due to the search property, all the elements in the search left subtree. In which case, if the tree is balanced, it's guaranteed the number of nodes over here will be about n over 2. It's really important to actually say that, right? Let me just write it down over here. There are many insights I'm talking about over here, so that's why you want to rewind the video and study carefully, right? It's very important to see that insight, to see the correspondence between the nonlinear and also the linear structure. They're really basically doing the same thing. Okay, let me write it down over here. Let's say if I decide to perform the search over here, let's say if I decide to actually go in this way, let's say the search may start with this and I decide to go here, and in that way over there, let me just say recurring on the right subtree reduces the search space by also half. Right, let me just highlight what you should really pay attention to. Reduces the search space by half because you effectively truncates this part of this tree. You simply don't need to look in that particular tree, because the tree presumably should be strictly larger than this root over here, meaning that there's no way it can be here. Otherwise, the tree is not really binary search tree. Alrighty, it's a very important insight. That's why I spent quite a bit of time actually walking you through the ideas about the thinking process. Let me recap very quickly. When we talk about performing a binary search tree on the array, the precondition is the array must be sorted. And the fact that this array is sorted, you can think about one more annotation over here. You can think about the sorted array is really corresponding to the in-order traverse output from the binary search tree. That's something you can also think about. Equivalent to the in-order traversal, right? The sorting property of a binary search tree over here. And when you do that, because it's guaranteed every time we simply go from the middle so that the left half and the right half are of equal size. So if you truncate one half, the other half is guaranteed to be reduced, is to be of the half of the size that we need to search for. That's why eventually we'll get to big of log n. In terms of the running time for this binary search, you can refer to the earlier lecture. And for the nonlinear structure over here, for the binary search tree, either this or this, it really has to be a balanced one in order to have the big of log n. Because if the tree is actually balanced, you can make sure every time if you choose to search or you try to recur on either side of the subtree, the other one that's ignored can be guaranteed to be about n/2. That means you can eventually also reach log n. And in this case here, for example, if I simply go to, for example, let's say from here, right, starting from here, if I simply go to the left, in some way I'm not really reducing the search space by half because most of the nodes are actually over here. So if I keep going this way, in that case, I'm not really reducing the size by half, right? I'll try to revisit this point again next week when I talk about the search property. But it's really important for you to understand the intuition here and also the table over here.